Okay, so it's our pleasure to have Eckhard Meinrenken from University of Toronto today to speak in our seminar. So Eckhard is going to talk about the differential geometry of weights. So please, Eckhard.
Yeah, well, thanks a lot for the invitation. It's a great honor to speak in this seminar. It's, well, partly also a great honor because obviously I'm not a non-commutative geometer. This will be mostly a differential geometry talk, but I believe that this theory of weightings has some significance in non-commutative geometry, at least in say, operator theory, particularly when it comes to things like hypoelliptic operators. So I would be interested in your opinion on that. And so let's do some of this theory. Oh, no, my screen is frozen too. What's going on here? Ah, okay. Well, so here's the plan for my talk. So I will first talk about the definition of weightings, what I mean by weightings. The idea is roughly what you would expect. You simply assign weights to coordinate functions. But my plan is to do all this coordinate free and see what we get out of it. So one thing we get out of it, this for me is kind of the discovery, is that there's an interesting weighted normal bundle appearing in this context. So a kind of normal bundle to submanifolds which takes weightings into account. And since there's a normal bundle, then you also have a notion of weighted tubular neighborhood embeddings. And there's going to be a weighted deformation space. So I guess this is what connects gradually things to non-commutative geometry. Of course, I have my copy of the book here on page 99. There's the famous tangent group point of Alan Kohn, which of course has had so much influence on our thinking. And so we were going to have some weighted analog of that, which has been developed in the context of hypoelliptic operators already, but we're going to see some new perspective on that, so to speak. So hypoelliptic operators come up a little bit when I talk about Lie filtrations in section 4, and then I'm also going to talk about some other generalizations. So all this is mostly based on this paper with Yannis, titled the same name as the title of this talk, Differential Geometry of Weightings. And some aspects of it are in this published paper also on Euler-Like vector fields and so on. Let's see if I can change sentence. Okay. Yeah, so let's get started with weightings. What do I mean by weighting? So to define a weighting, the first thing is motivation. So what are some motivations for introducing weights for coordinate functions? Well, there's lots of contexts where you would want to have normal forms with weights. So this appears a lot in singularity theory. For example, if you look at equations like y squared minus x cubed equals 0, things like that. It also appears in symplectic geometry. That's sort of my interest, where sometimes you have things that vanish linearly in some directions and quadratically in other directions. And there's certainly many other contexts where this kind of idea appears. Of course, it's also familiar in context of weighted blowups, which mostly used in algebraic geometry, but also a little bit in differential geometry already. And then, as I mentioned before, in the theory of hypoelliptic differential operators. So last December, there was a talk by Yakovos Androulidakis, who talked about hypoelliptic differential operators, and in particular, this so-called Kolmogorov operator. And you see this Kolmogorov operator, so this is an example of a hypoelliptic differential operator, which is of mixed degrees, but it becomes of degree 2, or for me, it would rather be of degree -2 if you assign weights. So if you say x has weight 1, y has weight 2, z has weight 3, then this would be of weight -2. So it's like a second order differential operator in this weighted world. All right, so to give the formal definition, we start out by fixing a weight sequence. So just a collection of non-negative integers. and let's say it's of order R when R is an upper bound. So if R is equal to 1, then you only have weights 0 and 1. If R is equal to 2, then maybe you assign some weights equal to 2, and so on. So R is, the order is kind of the upper bound for the weights. And the idea is to assign these weights to local coordinate functions and use this, so to speak, as a model. So our first definition of weightings, maybe not quite satisfactory, is the following. We say an order R weighting of a manifold M along a submanifold is a filtration of the algebra of functions. So a descending filtration. Think of these subscripts as order of vanishing, but in a weighted sense. And the way we make sense of weighted sense is that in local coordinates, so on some coordinate patch, the part of filtration degree I consists of monomials that have weight at least I. Yeah, and the first part in the filtration should be just a vanishing ideal of the submanifold. So any questions about this definition? I should say this definition, after we worked out all the theory, I asked around if people have seen similar contexts. And of course, then I learned that basically the same idea was already introduced by Richard Melrose in unpublished work in 1996 under the name of quasi-homogeneous structures. So this is unpublished work, a little bit incomplete, but it was recently completed in a thesis of Baer. So there's some kind of independent approach to our theory of weightings, which goes under the name of quasi-homogeneous structures. All right. So let's go some examples. So first of all, if R is equal to 1, the order is equal to 1, then as I said, you only have weights 0 and 1. And then these ideals in the algebra of functions are just the kth power of the vanishing ideals. So it's just the usual kth order of vanishing along the submanifold N. When R is equal to 2, it turns out a weighting is equivalent to simply having a subbundle of the normal bundle. So that's actually equivalent. So the way it goes is, so the filtration degree 1, as always, has to be the functions vanishing along N. Filtration degree 2 is the functions that vanish along N and whose differential vanishes on this subbundle. And then the higher ones are just determined by taking products. I should emphasize the filtration, of course, has to be compatible with the algebra structure. That's the filtration as an algebra. So this is filtrations of order R equals 2. Now for higher order, well, one thing I can say is that if you have a nested sequence of submanifolds, say R different submanifolds starting with your given submanifold N and ending with your ambient manifold M, that determines an order R weighting. So yeah, filtration degree 1 is whatever vanishes on N0. Filtration degree 2 is whatever vanishes on N-1, together with all the products of things of filtration degree 1, so things that have to be there anyway, and so on. That's how it goes. So this is one way of describing a weighting of order R, but of course this is kind of inconvenient, and these choices of submanifolds are highly non-unique.
So Eckhard, sorry
Yes.
to interrupt you. There's a question in the chat. You ask about, are the filtrations filtered by ideals?
Yeah, they're ideals, yes. Because the filtration starts in degree 0, it follows from that. Because it's compatible with the algebra structure, they're all ideals. Right. Yeah, so basically our question now goes towards how can we describe these weightings in a more coordinate-free way? I mean, I just described in terms of this local model. Well, one thing we can say is right away is that any weighting of order R also determines a decreasing filtration of the normal bundle, right? Because you have this filtration of the algebra of functions, and the first part is just the vanishing ideal. So you get a filtration of the vanishing ideal in particular. And vanishing ideal mod its square is the conormal bundle, sections of the conormal bundle. So you get a filtration of the conormal bundle and dually of the normal bundle. So there's always this filtration of the normal bundle in the picture. But unfortunately, or fortunately, this filtration of the normal bundle is not enough. So basically what goes on here is to know the vanishing ideal, it's enough to know F0. To know the next one, it's enough to know F minus 1. But if you want to have it in degree 3, then F negative 2 is not enough. You need somewhere like a second order approximation to a submanifold. So having a subbundle is like having a 1-jet, and you rather want a 2-jet. So this is approximately what's going on. So if you compare to what we had on the previous slide, having the sequence of submanifolds, that's just way too strong. Having just the sequence of subbundles for the normal bundle is just way too weak. So we need something in between, and how to pin down exactly what you need. It took us a little while. Any question? Okay, so this is our question now, how to describe weightings in a coordinate-free way. Right, it can be done in terms of this filtration directly, but the answer we came up with was in terms of jet spaces. So what we take as our starting point, motivated by what I just said, is we look at the rth tangent bundle, a higher order tangent bundle. So this is the fiber bundle consisting of r jets of curves. So basically, if you write local Taylor approximations, then it's the rth order Taylor approximation of curves inside M. One thing maybe I should warn right away is if you're not familiar with these higher tangent bundles, is that they're not vector bundles. If you teach a course in differential geometry and you use the curves definition to introduce a tangent bundle, you always run into this problem that the curves definition doesn't really tell you why it's a vector bundle. And for these higher ones, they really are not vector bundle. Anyway, these higher tangent bundles enter our game. And one basic ingredient of the differential geometry of these higher tangent bundles is that functions on the base M, they have all kinds of lifts. So if you maybe think back first for the usual tangent bundle, if you have a function on the base, there are two ways of lifting it. You can simply take the pullback, or what you can do is you can take the exterior differential of the function and view this as a function on the tangent bundle using the pairing. So for the higher tangent bundle, there are different lifts. And one way of looking at this is simply you apply the function f to a curve, and then you look at the Taylor coefficients at t equals 0. So these superscripts have multiple meanings. So, on one hand, it's like the terms in Taylor series. It also signifies, so to speak, the abstract ith derivative of the function. And it also indicates homogeneity. So on the rth tangent bundle, there is an action of r by rescaling of curves, and f upper I is homogeneous of degree I. So all this is kind of encoded in this index. Anyway, so all these lifts one has. And yeah, so first observation is then the following. If you have an order R weighting along the submanifold given by this filtration on the algebra of functions with weighted order of vanishing, this determines a subbundle of the rth tangent bundle along our submanifold. And the way it's determined is, well, you look at the functions of filtration degree I plus 1 and look at their ith lifts. And yeah, this subset which is cut out by those lifts, that's this Q. So first observation in this work with Yannis is that if you have an order R weighting, it determines this subbundle, and conversely, by basically the same prescription, you can go back and recover the filtration from that. Yeah, the weighting, huh? So the filtration of the algebra of functions. Now, of course, this doesn't quite answer the question of how to define weightings in a coordinate-free way, because now you have to answer which subbundles of the rth tangent bundle correspond to weightings. And yeah, this took us quite a while to figure out, and eventually we came up with the following answer. So instead of just looking at lifts of functions, we also have to look at lifts of vector fields. So if you have a vector field on the base, it also has all kinds of lifts to the rth tangent bundle. There's this x0, which is called the tangent lift, but then there are all kinds of vertical lifts. The easiest way of saying what these lifts are is to say what it does on these lifts of functions. So if I take the negative I lift of x applied to the Lth lift of f, it's vector field applied to f, lift L minus I. So it just goes well with the homogeneities, and these factorial factors in front you can pretty much ignore. So x0 is some vector field which, which, as I said, is called the tangent lift. Because if you have a diffeomorphism on the base, it lifts to a diffeomorphism on the rth tangent bundle. So infinitesimally, that's the generator. All these higher ones, they're all vertical vector fields. So TRM is a fiber bundle, and so they're all tangent to the fibers. Yeah, and all these lifts, they span a subalgebra of the vector fields on the rth tangent bundle. And this subalgebra plays a role. And here's then our answer. So a subbundle of the rth tangent bundle corresponds to a weighting if and only if two things are true. So first of all, it has to be invariant under reparametrizations of curves. So on the rth tangent bundle, one has an action of R, as I explained, by just rescaling of curves, but there's a bigger monoid that's acting just reparametrizations of curves, and has to be invariant under that. And secondly, it has to be an orbit of this graded Lie subalgebra that I just described. So there has to be a subalgebra of these x upper i's, which kind of span the tangent bundle everywhere. So this is the condition. It's the best we could come up with, and actually not so easy to prove at the moment. So I'm still hoping to maybe find a nicer way of saying what weightings are.
You say it has to be an orbit. I mean, it has to be invariant, or it really has to be an orbit?
In orbit, yes, or a union of orbits.
Oh, union of orbits. Okay.
Yeah, so it doesn't have to be connected necessarily. A finite union of orbits, finite union of orbits. Yeah. So it's, I mean, another way of looking at it is that it's these lifts of vector fields, they give a foliation of TRM, and so it's like some leaf of that foliation, or a collection of leaves. Right. Yeah, one good thing about this construction is it's nicely functorial. So if you have two manifolds with weightings, there's an obvious notion of weighted maps, right? It's just a pullback map should preserve filtrations. And it's very easy to see that this is the case if and only if its rth tangent lift is a bundle map with these Qs. It takes bundle to bundle. And this is somewhat useful viewpoint, in my opinion, because it allows you to formulate various compatibilities with other structures. For example, if your manifold is a groupoid, then you would like to say what it means to be a multiplicative weighting, to be compatible with the groupoid structure. So in terms of these filtration on functions, I'm not so sure how easy it is to say it, but in terms of this characterization with a Q, it's very easy. You just say that Q should be a subgroupoid. That's all. All right. So far about definition of weightings. Now comes, unless there are further questions, that comes now the next topic, which is this weighted normal bundle. Okay, weighted normal bundle. So our observation is that if you have a weighting along n, defined either in terms of this filtration on the algebra functions or in terms of this subbundle Q of the rth tangent bundle, this determines a fiber bundle along the submanifold, again with an action of this monoid of multiplicative scalars. So there's a scalar multiplication on it in such a way that the associated graded to our filtration of functions are exactly the homogeneous functions of degree k. So you might say the polynomials of degree k. So in plain words, or in other words, we take the associated graded of this filtered algebra, then we have a grade algebra, and then we take its spec, the homomorphism into R. I should say that this viewpoint was very much, of course, influenced by my reading of the paper of Nigel Hickson and Harsh Sadek. So to use these spec definitions even in C-infinity differential geometry. So we call this the weighted normal bundle. So if the weighting is trivial, then this really recovers the usual definition of the normal bundle, or one of the many definitions of normal bundle. So you can basically see this is definitely the right definition. What makes it a theorem is that this really becomes a smooth fiber bundle. So that's very good. But the first thing to say is it's not a vector bundle, right? It has this action of the monoid of scalars, there's a scalar multiplication on it, but it's not a vector bundle. This is similar to what we had with this rth tangent bundle, which is not a vector bundle. There's this scalar multiplication action on it, but it's not a vector bundle. So it's what's now called a graded fiber bundle. So this theory of graded fiber bundles was developed in the work of Grabowski and Rodkiewicz. And it turns out to be, might say, surprisingly rich and interesting. The name and also the theory comes a little bit from supergeometry. So if you recall supergeometry, initially people were talking about Z2 graded manifolds. But then it became interesting and fashionable to also look at Z-graded manifolds. And if you take a Z-graded supermanifold, but just take the special case where everything is even, then you end up with this notion of a graded fiber bundle. So in the sense, it's super geometry back in ordinary differential geometry. So one of the interesting things one can do with graded fiber bundles is that it's a linearization factor. So if you have a graded fiber bundle, then you get a graded vector bundle. Graded vector bundles, of course, are special cases of graded fiber bundles because they have an action of multiplicative scalars. Not the vector bundle multiplication, but the graded vector bundle multiplication. So with different weights and different summons. And this linearization functor is simply the normal bundle functor. So given such a graded fiber bundle, you can take its normal bundle relative to the zero section. That's a vector bundle like any normal bundle. And yeah, the original action of the monoid now linearizes to an action of monoid and it's compatible with a vector bundle structure. So this becomes a graded vector bundle. So questions, of course, what is this for our weighted normal bundle? And it is what you would expect. So if you remember earlier, I mentioned that the usual normal bundle, if you have a weighting, inherits a filtration by subbundles. And you can look at the associated graded bundle. So this associated graded bundle is this linear approximation of this weighted normal bundle, of the nonlinear thing. Right, and you can also describe this weighted normal bundle in terms of the Q which sits inside TRM. It's a quotient of this fiber bundle Q. So this is analogous to the more familiar definition of the normal bundle, where you just take the tangent bundle restricted to n and then take the quotient by Tn. So the Q basically plays the role of rth tangent bundle restricted in the weighted sense to submanifold n, and then we take some quotient. So this all works very nicely. Right, and then as I said, there's also a weighted deformation space. Unsurprising if you look at this definition in terms of filtrations. So weighted deformation space, just like the usual deformation space for a submanifold, is you take the weighted normal bundle together with m times non-zero real numbers. So basically you think of this as a family of manifolds sitting over the real line. Over each non-zero number, you put a copy of m, and over the zero fiber, you put the normal bundle. And in our case, the weighted normal bundle. So this picture indicates the usual deformation space for S1 relative to a point. I think that's the best I can draw. Weighted normal space I can't really draw, but in any case, this is what it is. And it comes with an action of non-zero real numbers, which is important in this context. It's called zoom action, which in the way of setup is as lambda goes to infinity, it kind of approaches the zero fiber and then goes off to infinity. The point of this weighted deformation space, of course, is the main point is that it's a smooth manifold. So it kind of blows up normal directions to n as t goes to 0, but in a weighted sense. So there are two ways of describing it. One is, again, as I learned from Nigel Hickson and Haj Sadek, is that you can describe in terms of the Riesz construction. So if you have a filtered algebra, then there's a corresponding graded algebra, the so-called Riesz algebra, and then you just take spec of that. So this is the algebraic definition. I'm not going to go further into that. There's also a more differential geometric characterization, I might say, which is basically saying what it does, what is it good for. Namely, if you have a function of filtration degree I, so vanishing in the weighted sense of order I, then it extends to a smooth function on the deformation space, which is homogeneous of degree I. So this subscript with a bracket I means that it's homogeneous of degree I. So that the claim is there exists a unique smooth structure on the deformation space such that every such function has a homogeneous extension. Right, so you put your function at the fiber at t equals 1, and then you extend by homogeneity, and the claim is that even to t equals 0 it extends. Right, that's the non-obvious part. So there's then some restriction to t equals 0, and this plays the role of an approximation of your function in a weighted sense now. So this is the homogeneous approximation. So if everything is unweighted, and for example, something, let's maybe go back and look at the case where the weighting is just trivial. If you have a function vanishing along n, this would be of filtration degree 1. And then you get a linear function on the normal bundle. That would be the linear approximation in this case. If you have something that's vanishes of order 2, then you get a quadratic function on the normal bundle. And you have the analog of this also in the weighted sense now. Okay, so you get these weighted approximations. Actually, you get these weighted approximations not just for functions, but you get them for all kinds of tensor fields. Right, so if you have the filtration on the algebra of functions, then it induces filtrations on the algebra of differential forms, on vector fields, and all those things. And the same story goes through. So particularly if you have a vector field of filtration degree I, then first of all, you get some extension to the deformation space of filtration degree I. So what I mean is you just put your vector field X on the fiber at t equals 1 as a vertical vector field, and then you extend by homogeneity. And yeah, it always extends to something homogeneous of degree I, and then you get something on the weighted normal bundle, homogeneous of degree I. So this is the homogeneous approximation. And same thing you can do with differential forms and just anything. Okay, so here's one example from symplectic geometry. Sorry about that. So if you have a symplectic manifold and an isotropic submanifold, which means that the symplectic 2 form vanishes along n, then one gets a subbundle of the normal bundle. Namely, there's this subbundle Tn omega, which is all the vectors that are omega orthogonal to the tangent bundle of n. And that contains Tn, so you can take the quotient. So that's the subbundle of the normal bundle. And as I had mentioned earlier, whenever you have a subbundle of the normal bundle, there's a corresponding weighting of order 2. So this you have here. And then you can check that the symplectic form omega relative to this weighting is of filtration degree 2. And because of it's of filtration degree 2, our story applies. And so you get a 2 form homogeneous in the weighted sense of degree 2 on the weighted normal bundle. And one can check using local coordinates, for example, that this 2 form is again symplectic. So that's one nice application. So again, even in this case, this weighted normal bundle is not a vector bundle. So this is some fiber bundle that's canonically associated if you just have a subbundle of the normal bundle. All right. Yeah, and then another thing I should mention is that if you have the weighted deformation space, then you immediately know how to define weighted blowups also. So for the unweighted case, this was nicely explained in the paper of De Boer and Skandalis, and it immediately just extends to this weighted setting. So what you do is you take the deformation space. It has this zoom action of non-zero real numbers. You have to so the zoom action is not quite free. You have to remove a subset, which is n times r, the submanifold times r, from the deformation space, then becomes free and proper. And if you take the quotient, then get the weighted blowup, or rather a doubled version of the weighted blowup. So you basically get the weighted blowup twice as a manifold without boundary. And if you take half of it, then you get a manifold with boundary, which is what people in C-infinity geometry would call the weighted blowup. I should say this of course works in a similar way. I mean, the whole story I explained also works over the complex numbers. There one wouldn't work with the algebra of functions, one would work with a sheaf, obviously, right? Because we cannot have global holomorphic functions. So you work with the corresponding sheaf. And instead of a real line, you look at the complex line. And then in this way, you can define the complex blowup. One difference is that then you encounter some orbifold singularities because the action is usually not free. Other than that, it all goes through. I find it somewhat strange that as far as I was looking, I couldn't find any treatment in complex geometry of weighted blowups in a coordinate-free way. So all the treatments I saw at the end of the day, they always use coordinates, which seems strange to me. Maybe it has to do with the fact that this weighted normal bundle indirectly enters the story and it's not a vector bundle. So this could be one reason, or maybe I just didn't look hard enough. All right, weighted tubular neighborhood embeddings. So we have this action of scalars on the weighted normal bundle. So there's some corresponding vector field on it, which is the Euler vector field. in coordinates. So if you use these weighted coordinates that I had in the very beginning, it's like the usual Euler vector field, except you have to stick these weights. We call a vector field Euler-Like in the weighted sense if it has filtration degree 0 and its weight is homogeneous approximation. So that's a vector field on the weighted normal bundle is this Euler vector field. So in coordinates, you would say it's the Euler vector field, the weighted Euler vector field up to higher order terms, where higher order terms is taken in this weighted sense. So here's a very simple example with R2. So the first example is weighted Euler-like because x d by dx plus twice y d by dy, that's the Euler vector field. And this y squared d by dx, that's a higher order perturbation because y has weight 2. So y squared d by dx would have weight 4 minus 1 is 3. So it's way more than the other parts. The other one is not weighted Euler-like because, again, y has weight 2, but x squared also has weight 2. So this wouldn't count as a higher order perturbation. Yeah, so for weighted tubular neighborhood embeddings, I need this observation that whenever you have this scalar multiplication action, there is a corresponding weighting to go with it. The scalar multiplication determines a weighting. And using this, we can define a weighted tubular neighborhood embedding to be a map of pairs. So from the weighted normal bundle into our manifold, which preserves the weightings, and such that its approximation, the weighted approximation, is just the identity map. So this makes sense because the weighted normal bundle of a graded bundle relative to its zero section is the weighted normal bundle itself. So this approximation becomes a map from the weighted normal bundle to the weighted normal bundle, and it makes sense to say that should be the identity. Right, and the theorem is that if you have a weighted Euler-like vector field, it determines a unique tubular neighborhood embedding. So weighted Euler-like vector field and weighted tubular neighborhood embedding is basically the same thing. So it determines a weighted tubular neighborhood embedding in such a way that the Euler-like vector field becomes the Euler vector field. So you can kind of linearize it in the weighted sense always. So that's basically the message here. Weighted Euler-like vector field and weighted tubular neighborhood embedding is almost the same thing, up to like completeness of vector fields and things like that. Outline of proof. I think I'm probably running a bit short of time. Maybe I'll skip the proof. Don't have to really know it. So let's just do the example. So here's an example of a weighted Euler-like vector field. So we take R2 with weights 1 and 2, and I have a higher order perturbation. And so for all natural numbers, this is Euler-like. Even for m equals 1, this would be a higher order perturbation because y times d by dx has weight 2 minus 1, which is 1, whereas the other parts have weight 0. Okay, and so this result had told me that there exists a tubular neighborhood embedding so that this becomes the Euler vector field. So another way of saying that in more down-to-earth terms is that it exists a coordinate change, at least near 0, such that this higher order perturbation just goes away. So it's linearizable. Right, so there should exist some diffeomorphism with this property, at least defined near 0. And yeah, it's true, and you can actually do it by hand. You can easily solve this exercise. This is explicitly the diffeomorphism that does it. Yeah, a more differential geometry example that I want to consider is back to the symplectic geometry. Sorry, this last symplectic geometry. Again, to isotropic submanifolds. So recall again, there's this symplectic normal bundle, which defines an order R2 weighting. And I mentioned the symplectic form becomes of filtration degree 2, so it has this approximation. Now what you can do is you can choose a primitive of the symplectic form defined near n, not globally, but near n. So I'm cheating a little bit here, which is of filtration degree 2. And then you, using the symplectic form, you can define a vector field, which if you count filtration degrees, it will have filtration degree 0. And checking, for example, in local coordinates or just linearizing this equation, you find this vector field is Euler-like. So it defines a tubular neighborhood embedding. Yeah, and this tubular neighborhood embedding has the property with a little argument that the pullback of the symplectic form under the tubular neighborhood embedding is the model symplectic form. So it's actually a one-line proof, which I should have included here. But in any case, so this is some small improvement of the Weinstein isotropic embedding theorem, because in the usual version of isotropic embedding theorem, one first uses connections and so on to turn the usual normal bundle into, to put a symplectic form on the usual normal bundle and then get this identification. So now we have this weighted normal bundle, which is completely canonically defined. And we use that as our model. And yeah, so with very little input, just this choice of this one from alpha, just this primitive, this already determines what the tubular neighborhood embedding is. Right. Okay, let's get to the Lie filtration, which is probably more towards the direction of the seminar. Okay, as you have heard when you attended Jacobus's talk in December, some types of hyperelliptic operators use this notion of Lie filtration on a tangent bundle. So a Lie filtration on the tangent bundle is filtration by subbundles with the property that if you take sections, so these are vector fields, it defines filtration on the Lie algebra of vector fields. And one thing one gets is that the associated graded bundle for this filtration becomes then a family of nilpotent Lie algebras. One way of seeing this, well, we have this filtration on the Lie algebra vector fields as sections of the tangent bundle. Then you get an associated graded bundle with a Lie bracket. And so this is a Lie algebroid with a 0 anchor. And this is this family of nilpotent Lie algebras. It's not the Lie algebra bundle, so the Lie algebras don't have to be isomorphic at different points. So in that sense, it's a family of Lie algebras. Anyway, you have this family of nilpotent Lie algebras, and because they're nilpotent, you can exponentiate them globally, and you get a family of Lie groups. And this is what's called the osculating tangent bundle in this theory of Lie filtrations. So I basically want to explain how to fit this osculating tangent bundle into our context of weightings. Yeah, first one example. So there's this Kolmogorov operator. In this case, the Lie filtration is spanned by vector fields d by dx and y being d by dy plus x d by dz. You can assign weights if you want, with x being of weight 1, y being of weight 2, and z being of weight 3. Then the h minus 1 is spanned by x, h minus 2 is spanned by x and y, and h minus 3 is everything. And whoops, oh, that's how you do it. And the Kolmogorov operator that at the very beginning, which Jacobus had in December, is the operator y minus x squared. So this is this hyperelliptic operator. So I'm claiming when you have a Lie filtration, then you get weightings in many ways. So again, you can use these lifts to the rth tangent bundle, but now we take lifts, the minus I lift of a vector field of filtration degree -I. And one observation is that, yeah, if you have a Lie filtration, this compatibility of with the Lie bracket means exactly that this spans a graded Lie subalgebra of the vector fields on the R tangent bundle. It turns out to be equivalent. I mean, it's very easy to see. So it's a nilpotent Lie subalgebra, and hence you can look at the corresponding group of diffeomorphisms, and you can apply this group of diffeomorphisms to the zero section, so you get a flow out. So this is then some subbundle of TRM. Well, you check that it's a subbundle, and again, one of these graded subbundles. So it's invariant under the action of scalars. Right, and so if you take the subbundle and just restrict to points, then this defines weightings for all the points. So every point has a weighting in this sense. And so you get a weighted normal bundle for every point. You might call it the weighted tangent space, and the union is the weighted tangent bundle, or called the osculating tangent bundle. So this is the same thing. Or you can also directly say it's some quotient of this P. So that's one set of weightings you can obtain, but there are other weightings that appear in this context. You can also look at nicely situated submanifolds of M. So they have to be somehow have to have clean intersection with the Lie filtration in some sense. So if it's a nice submanifold, then that submanifold inherits a weighting, and then again you get a weighted normal bundle. And so this is basically what got me sort of started on the subject, trying to understand this kind of non-linear normal bundle that appeared in the work of Hodge and Hickson, and try to understand it differentially geometrically. So my confusion was here that well, if you have this this kind of non-linear normal bundle, it shouldn't really matter what happens far away from the submanifold. So what exactly do you need? And yeah, so the answer is that you need a weighting. Right, so there's also an osculating tangent groupoid. So what you have to do is you have the Lie filtration on M, and can take the product Lie filtration on M times M. And as I said, on nice submanifolds, you get weightings, and it turns out the diagonal is actually nice. So you get a weighting along the diagonal, and then you have the weighted normal bundle. And it turns out the weighted normal bundle again is the weighted tangent bundle, is this osculating tangent bundle. It's the same thing. Right, and then I can go back to the definition of weighted deformation space, and so I get the corresponding weighted deformation space. I should have written here. So this is the osculating tangent groupoid. Sorry, this is a typo. We get a weighted deformation space. So this, of course, was introduced in the context of Lie filtrations by Choi Ponge and Van Erp Juncken and Hodge Hickson and Mosen. And yeah, so whenever you see a lineup of people, you kind of want to get in line. So hopefully we can add ourselves to the line. Yeah, no, of course, this weighted deformation space, this osculating tangent groupoid is very useful. It was used in the work of Van Erp and Juncken to develop a pseudo-differential calculus in this context of Lie filtrations. So with their applications to hyperelliptic operators. Along the work of Dabor-Skandalis, who had done similar things for the non-weighted tangent bundle. So Dabor-Skandalis explained how to understand pseudo-differential operators in terms of the tangent groupoid. And Van Erp and Juncken generalized this to the hyperelliptic case and some other contexts. So basically, one more step you can try to do now is to understand this also in terms of conormal distributions, right? Pseudo-differential operators are basically conormal distributions along the diagonal. And so now we have this notion of weightings along submanifolds. So we want to develop a notion of weighted conormal distributions along weighted submanifolds. So this is work in progress with my student, Dan. Okay, a few more directions I want to mention. So where do we actually need that these HIs are subbundles? One actually doesn't need it very much. So you could directly start with the filtration on the Lie algebra of vector fields. So not take them to be subbundles of sections of subbundles. Directly use a filtration on the Lie algebra of vector fields. So this goes under the name of single Lie filtration. Here I'm actually allowing even an H0 in a sense, like why not? So if you only have H0, then this is kind of the modern definition, Androulidakis and Skandalis, of a singular foliation. So a condition we need is that all these components are locally finitely generated by finitely many vector fields. And there's also some kind of sheaf-like condition one needs, which I skipped here. So if there's only H0, then it's a singular foliation. And so we've combined here the notion of singular foliation with the notion of Lie filtration. So things like this appear in sub-Riemannian geometry. So there's this so-called Martinez-Carnot structure, which is an example of a single Lie filtration, which does not come from a Lie filtration. So one takes H, as I've written here, spanned by these two vector fields, and then you obtain the Lie filtration just by taking brackets. And so if you just take one bracket, then I think it's not a section of a vector bundle. In that sense, it's singular. So singular Lie filtrations have been obtained, and I think that's also work in progress by Androulidakis, Van Erp, Most, and Juncken, who are generalizing their earlier work on Lie filtration now to these singular Lie filtrations with applications to hyperelliptic operators. Again, as presented in Jakovic's talk in December. I wasn't there, but I watched the video. Okay, yeah, anyway, so the singular Lie filtrations, they also give lots of examples of weightings. So just like I explained before, now you get not a foliation of the R tangent bundle, you get a singular foliation. But again, you can look at leaves of this foliation, you can look at flowards of submanifolds. And yeah, so typically these will then, I shouldn't say typically, if the submanifold is nice, some clean intersection condition, then you get weightings. And so there are lots of examples of weightings which arise in this context. So in particular, we have weightings along points if H0 is equal to 0. Okay, and as a final thing I wanted to mention, there's a generalization to what we call multi-weightings. So you can look at settings where you don't have to have one submanifold, but say two cleanly intersecting submanifolds or more submanifolds. So clean intersection of submanifolds, of course, means that the intersection is a submanifold and the tangent bundle of the intersection is the intersection of the tangent bundles. One knows that one can introduce local coordinates, so that looks like intersection of two subspaces. And then one can consider bifiltrations, so weighted order of vanishing on one submanifold and weighted order of vanishing to another order on the other submanifold. And if you do that, so you get a bifiltered algebra, and then you can obtain a double normal bundle by looking at the associated the associated bigrade algebra, and then take its spec. You get a double normal bundle. You get a double deformation space, which now lives over R2. You get double tubular neighborhood embeddings, double tangent groupoid with a double tangent bundle, double weighted tangent. So all kinds of things like this you can do, all kinds of nonsense. And the same thing you can do with multiple k-fold intersections, which are clean, by which I mean that locally you can introduce coordinates so that it looks like intersection of coordinate subspaces. Yeah, and I guess I finished right on time. This is all I wanted to say.
Thank you very much.
Thank you.
Any
I don't know
questions?
who's in charge now. Oh,
comment?
Shuang is in charge. Please go ahead.
Okay.
No, please.
Nigel, please.
Thank you very much, Eckhard. Are there any questions?
I have lots of questions.
I have a remark. You said you see a line. It's always good to join a line. You always want to join a line if you see a line. And it reminded me of something that happened to Yakovos. He was in Tokyo. He wanted to go to the museum in Ueno Park, the archaeological museum. And he saw a line. He thought, it's the line for the tickets. I'll join the line. It was a very long line and it took a long time to get to the front. And when he got to the front, he discovered it was not a line for the tickets. It was a soup kitchen. But, you know, he'd been in the line a long time and he was hungry by then. So, so it's not always good to join a line. Any real questions?
Can I ask a question? It's actually also related to Nigel's work about Getzler scaling in terms of the tangent groupoid. Does that fit into the framework of these weightings?
I'm sure it will, but I mean, this is certainly one of the questions I also have. This is maybe one reason why I introduced these or mentioned about the multi-weightings. Mm-hmm. So you could have a weighting. So if you have a vector bundle, then you could have some interesting weighting on the base, but then you have a vector bundle over it, and you might still want some interesting weighting on the vector bundle as well. So now you're kind of dealing with two weightings.
Mm-hmm. Okay, thank you.
So I would imagine it should fit into this context.
Okay, thanks.
I have some comment or suggestion. I mean, I cannot say I know the recent developments, but somehow, you know, the way this fits very well in non-commutative geometry is that once you have something like the tangent groupoid or an adaptation of that, then, you know, there is a corresponding relation between like the structure, if you want, of the cotangent space. I mean, as a bundle of groups, but of course, I mean, in a more refined way, as in your case with weight. But and what happens with the deformation when you deform it essentially to a point, and I mean, this deformation, which comes from the tangent groupoid, encapsulates geometrically the index theorem. Now, when you have a refined setup like the setup in which you work, what it means is that you will be able to deal with hypoelliptic operators, of course, and so on. But that somehow, when you want to obtain an explicit formula in differential geometric terms for the index and so on, it should be very profitable to use cyclic homology. Mm-hmm. And if you want to use the refinements that you have on the tangent groupoid coming from the additional structures that you have in order to obtain explicit formulas which will be much more special in that framework. So I think this is the way in which it connects very strongly to non-commutative geometry, what you have explained.
Mm-hmm. Thank you.
I have another question about tangent groupoid. Let's say for the weighted structure that comes from this Kolmogorov operator. In the work of, I guess, Kolmogorov, but also Bismuth, where this operator arises, it becomes very important to study the vector field and the vector field, this funny vector field which appears in Kolmogorov's operator, x ddz, I guess it was in your example. And so that's like the geodesic flow in the Kolmogorov example. Is there any way you see the dynamics of this vector fields in any of the geometric objects you construct in this tangent bundle, this tangent groupoid? Does it see this particular vector field x ddz in an interesting way? So there are two vector fields. There's ddy, and then there's x ddz, and it's really the x ddz term which appears as the order 1 term in Kolmogorov's operator, which is much more geometrically interesting than the quadratic terms in Kolmogorov's operator.
Yeah, I'm sorry, I don't think I have any answer to that.
So all of the, if you have one of these Hohmann systems with a collection of vector fields whose Lie brackets generate, let's say, the tangent bundle, all of the vector fields are somehow the same from your point of view. They're all treated equally, the ones which appear quadratically in the operator, and the one which appears
different homogeneity, and
that's true.
I guess the rescaling goes different, right?
Yeah, okay. Any other questions for Eckhard? Sean, please.
So Eckhard, so in your example, you had this example from isotropic submanifold. So how about the co-isotropic ones? Do you get this?
Yeah, that's a very good question. I mean, from viewpoint of symplectic geometry, one asks immediately, so what about in general constant rank submanifolds, because there are normal form theorems for that. And somehow, I mean, the story as such doesn't seem to fit there, because the true form does not vanish along n in this case. And yeah, I've been trying to think if there's some generalization one can do, but I couldn't come up with anything. And of course, in the co-isotropic case, there's also, I mean, you see there's additional structure then to the submanifold, because then one has this foliation of the submanifold. Whereas in my context, I always have no extra structure on the submanifold itself. So yeah, I mean, this is a bit puzzling to me also, that now we have an even nicer version of the isotropic embedding theorem, but so far for the more general constant rank embedding theorems, I couldn't find anything.
Thank you.
Any other questions? If not, then let's thank Eckhard one more time, as much as we can over Zoom. Thank you so much.
Yeah, thanks for listening.
Any announcements from our chief, Masoud? Anything for us?
There will be a talk next week for sure.
Okay, great.
Thank you all. Thanks, Eckhard, for a nice talk. Thank you.
So can I add a kind of announcement? I think the Asia Pacific node is starting on March 1st.
Oh yes, great. That's right. Yeah. This I should have said that. Yeah.
And those talks will be announced in the same.
Yes.
Emails. Yeah, in the same way.
Yes. Same email, same website.
There is a talk by Joachim Kunz that is already announced in our global site.
It's on the site. Okay, thank you.
Okay, thank you.
Excellent. Thank you very much, everyone. See you next week.